you run maze.java. So you run maze.java and you'll get this. Okay, and what this does is that this designs a very simplistic maze, which I'll go over the code in a bit, and I think the videos went over the code a bit. But essentially, this maze was generated by simply each of these squares is represented by a cell object, which have a north wall, which have 4 booleans: north wall, south wall, east wall, west wall. And all that these do, and all I did to create the maze, as I'll show you in a minute, was just I flipped a coin and I said, hey, if it's heads, remove my north wall. If it's tails, remove my west wall. And my north wall is somebody else's south wall, and my west wall is somebody else's east wall. And so I just simply did that. And then the objective is to get from here to here. And the reason I did that was just a very easy algorithm to make sure that there was always a solution, right? And so your solution should look something like this, right? And the maze is always randomly generated, so I'll compile this, run. So this is what the solution should look like. So go from the top left corner all the way down to the bottom right corner. Okay. Now the gray area that's grayed out is area that my algorithm tried to go to, but didn't find a solution, so it had to backtrack. So it was simply keeping stuff. So it was making stuff a different color. So let's take a look at the code of maze grid panel, because most of the you really only have to do one method. You have to write the solve maze method, right? Which I started off for you. But let's go ahead and just check how I let's go ahead and just actually look at the building blocks of this first. The building blocks of each cell of the maze is that everything's in a cell. A cell is just a J panel, which means it's just basically a window element in there. It's a small, you don't really have to know too much about it, other than basically that Java knows it can draw J panels. Okay? There's a north wall, a south wall, an east wall, and a west wall, just simply variables I made up. It also has a row column, basically saying where it is in the maze. And then this was just simply, let's just check the constructor. Constructor is very simple. I give it a row and a column. I set the row and column to be row and column. I say, hey, I have this function that JPanels have called this.setBackground, which is really the only function you need to know about graphics for this purpose of this project, which says, hey, the background of this cell, make it white. Color.white, and you'll notice that there's a bunch of other colors. There's like, you can do color.red, color.black, any kind of common color there. This you don't need to know so much, which is just simply paint component, which was used for drawing the maze. And all that did was basically, if you can guess, hey, int xy, this got get width, height. And what it did is that basically it would, if I'm the north wall, draw a line on my north. If I was the south wall, draw a line on my south side. If I'm the east wall, draw a line from my east side to my, draw a line on my east side. And that's all those 4 lines do. It just simply makes it so that it can draw its walls. You don't have to ever worry about that or mess it, but that's what that function does. So how does the maze get drawn anyway? Well, a maze grid panel, its constructor takes in the number of rows and the number of columns we want. I simply say that the preferred size of the panel is an 800 by 800 pixel, right? So that's how big it's going to be on your computer. And I say that it's going to have this many rows and this many columns. I then use a function called setLayout, which basically says, hey, I'm going to have a bunch of panels. I'm in fact going to have this many panels, row by column. So I want a row by column grid layout for panels. This just simply puts it in a grid, like as you would expect a maze to be. And then I say this.maze is equal to a new array of cells. So the internal representation of the maze is a bunch of cells, right? Those cell objects we just created. So it's a new array. And then what do? I go through each one of those. and I say, hey, I'm putting these mazes I'm creating a new maze object, a new cell object for each row column position. And then I add it to the maze grid panel, and that will just simply automatically lay it out for me because I'm using the grid layout. Okay. Then the constructor calls this.generate northwest maze and this.solve maze. So generate northwest maze, what that went through was just simply say and generate all the walls. What it did is that it went through all the rows and columns and it said, hey, if it's 0, 0, don't remove any of the walls. Because one of the things I did is that I made sure that if there is a, I made sure that when I give you this thing, even though you can't see it, there are walls all along the border, so you don't have to worry about going out of bounds if you're paying attention to your walls. So you can ignore the location and just make sure you're in the walls. In the bounds. You're not going out of bounds of the wall. Okay, so for int row is equal to 0, row is less than number of rows, right? We go through and I simply say, hey, if the corner is blank, just leave it open. Otherwise, if the row is 0, I just simply, if I'm on the top row, I just remove all the east-west walls, right? So when I remove my west wall, I'm removing the other guy, the guy to the left of me, his east wall, makes sense. And if I'm in the column, if I'm in the first column, I remove the north-south wall. And this is just simply to make sure that there's something, a solution all the time. Then, as I said, otherwise I flip a coin, and if it comes up heads, we remove our north wall, otherwise remove the west wall. And then we repaint the, basically I redraw it. And then I redraw the whole thing when we're done. So, all right. So how the other thing I have is that basically I have a visited function. Given a row column, right? Given the row and column of a cell in a maze, I get the background of it and I ask, hey, is it white or red? If it is white or red, then we haven't been there before. Those are the colors I use to say, hey, you haven't been somewhere in the maze yet. Otherwise, I return true to say it's been visited. So how in the world do you maneuver things in this maze? Well, it's actually fairly straightforward. I'm going to go ahead and do something very simple. So we start at 0, 0. So I'm going to go ahead and say, I'm just going to write a for loop here, but as you can see, I have some commented out a while loop for you. For int I is equal to 0, I is less than 5, I plus plus. So in other words, I'm just writing a loop, and I'm just going to execute what's in here 5 times. Okay? That's all I'm going to do. So let's go ahead and see. Let's go ahead and see stack.push let's see. So the first thing I'm going to do is I'm going to get my current cell by going and saying, hey, cell current is equal to get stack.peak. And then what I'll do is that I'll mark it visited by going, hey, current.set background color.green. And then, regardless of anything, I'm just going to move south by saying, hey, stack.push, see. All right. Current.row -1 current.col. And that's all I'll do. I'm going to do that 5 times. So I'm going to go ahead and compile this. So let's see what that does. sorry. 1 second. It says, hey, required cell. Stack.push. Oh, of course. My bad. Stack.maze current. There we go. Current row 1, current column. Right? It's got to compile now. There we go. Oop, out of bounds. -1 for, oh, right. -1 is north. My bad. -1 is north in this, right? Because y coordinates. So row -1 goes up 1. So to go down, I need to go +1.
Sorry, I'm confused.
What?
Why is it -1 is more?
Aha! So graphics 101 for your graphics 101 for coordinate locations. You are probably familiar with the coordinate plane being thus,
Yes.
right?
I know that.
Okay? Well, it's wrong for computer science at least. In computer science, this is the coordinate plane over here. This one, the one with the big X on it. Instead, what we do is that we let origin be the top left corner. The X coordinates are just act as normal, but increasing the Y goes down. This means that the top left of your screen is 0, 0. Okay? And that means that basically that if that means that 10, 0, well, sorry, my bad. 0, 10 is 10 pixels down on your screen. Now, furthermore, this is complicated by the fact that I'm not used that arrays use row column notation. So my current row is +1. So, and rows go down. So now, oh, I didn't compile again. This is what happens when I don't use an IDE. Doesn't catch errors like that. Here we go. So what I did is that I went 1, 2, 3, 4, 5 steps down. All I did was I pushed something onto the stack, and then I peeked at the stack to see where I currently am, and then I colored it, and then I went 1 down. Okay? So this would just keep going down and down and down and down until I hit something. Now the other thing I can do is that I can use a let's go ahead and see what I can do. So I'm going to go down once. Okay? Let's say I'm going to go, actually, let's say I go down 3. And then I'm going to say 4. Now, your actual solution should look nothing like this. I'm just using it for the point of illustration. 4 int I is equal to 0. I is less than 5. I plus plus. Cell current is equal to stack dot peak to get where we are in the stack.
Wait, I thought peak is like we're just looking at.
We're looking at the top. So we're not going backwards. What we can do with backwards is that we can, I'll get to that in a second. I'm just going over the basics of
I see.
of how we're maneuvering stuff. Okay, where we currently are, make it green, please. And then, I mean, you can use whatever color you want. And then I'm going to say, rather than pushing, so what we're doing is that we're pushing the next place you want to go on the stack. And rather than pushing +1 on the row, we're going to increase the column by 1. And what that will do, so it's the same thing as the previous one. The only thing is that I've just changed the +1 over here from being over here to over here. And this will be to illustrate a point. Because I'm just teaching you the basics of maneuvering this, and then I've given you the algorithm. So your goal is to basically translate both, or is to adapt both. So notice over here I went down, and then it went to the right by going +1. Notice also that it crossed a wall, right?
Yeah.
Because that's what I told it to do. Or rather, I told it to not care about walls. Walls are just there to be drawn, right? So you can go through walls, but that's not going to give me a good solution, right? If I go down, right, I mean, technically, if I do this, hold on one second. If I do this, right, it's 20 by 20, so if I do 20 and then 20, right, and then I recompile, you can guess what's going to happen. Compile, run it. 19 is out of bounds. Oh, index is out of bounds. 20 is out of bounds, it says. So perhaps we need to go 19 by 19, right? Yeah, we just needed to do it 19 times and 19 times. My bad. Compile, run. Okay, and notice, right, you can't say that this is a solution to the maze, right? Because it, of course, is going through the walls and ignoring the walls. So instead what we'll do is that we do have to put in some knowledge about the walls. And checking to see if a wall is very simple. You just simply say, hey, if current dot, so basically all I have to go and say, hey, if current dot east wall, if I want to go east, right, I just simply say, hey, if there is not an east wall there, then I can go that way. Also, when you're accounting for backtracking, you'll want to check if it's been visited or not, but let's go ahead and compile this and watch what happens. F8 and F5. Run it, and notice that basically it doesn't go left, it doesn't go to the right at all now. Let's go ahead and generate another maze, because again, this is totally, these are generated totally at random. Okay, so now it stopped at the wall, right? So if we use the west, so if we use basically simply saying, hey, if current has a wall, has an east, west, or north wall, or whatever direction wall, then I can't go there, which is super useful. Okay. And the reason we color stuff is that basically that we can keep track of where we've been, and then we can color stuff a different. As you remember from my stuff, I was coloring stuff gray to note that where I'd been. So let's go ahead and take a look at the assignment write-up for a second to get more of an idea here, now that you understand a bit more how to move things. All right, so the basic mazing solving algorithm is actually fairly straightforward. It's like being, if you're familiar with the Greek fable of Theseus and Ariadne and the Minotaur, right? The entire idea of getting through the labyrinth is that Theseus was given a bunch of thread by Ariadne. And so we're just simply giving we're giving basically ourselves two tools. The stack is our thread to wind through the maze to make sure we are where we have been. And then we're also able to color the walls of the maze, the background, right? If you have basically a long rope and chalk, this becomes incredibly useful for getting through mazes because you can mark wherever you've been. And then you use a very simple algorithm, which is that I'm going to go down a corridor until I get to a dead end. And I'm going to mark every corridor I go down. So if I ever come to a selection, I'm just going to choose if I can go this way or this way. I'm going to maybe just say, hey, if I have a choice between going left, forward, or to the right first, I'm going to go ahead and mark I'm going to go try left first. So I'll mark that wall, and I'll keep doing that, marking walls until I get to a dead end. At that point, I back up using the thread until I get back to a choice. And I know I haven't gone this way, I know I've gone this way because I marked it, but I haven't gone this way or this way, so I just go and say, okay, now I'm going to go north, or whatever this direction is. now until I get to a dead end. So that's how the algorithm works. The basic maze solving algorithm works. Push the start position to the top of the stack, which is something I already do for you in the program. Right? Push it to the start of the start position to the start of the stack. That's everything I'm doing there. Over here. And then we use a while loop. While the maze exploration is not done and the stack isn't empty, we can peek to get our current position. So that's what my while loop is over here. While, and you'll have to figure out the best way to say it's not done. But when in doubt, just simply like try 50 steps or something, like, and try going through it for 50 steps, right? Because you can figure out the while loop, the correct ending condition later. While cell dot, so we get the current cell, and then I give you 2 hints about how to use it, right? You can grab the current cell by going or by using current.row, current.column, and you can get stuff by doing -1 or +1 to these. Anyway, but we get our current position, and if we can go north, and we haven't visited there yet, we push the location to the stack onto the stack, and we color it. Otherwise, we can. Else, if we can go south, we try it that. We do the same for east and west. So basically, once you figure out how to go in one direction, all the other directions go into place. Now, if you can't go in any of the directions, because you've already visited anywhere, there's no choices. We can't go anywhere, so we're at a dead end. Mark the current position as a dead end. You do that by setting the color to gray or something, and then pop the stack. Because what you've been doing is that you've been keeping track of where you are on the stack. Every time you move, you push onto the stack. Your current position is at the top of the stack. So when you pop off the stack, you immediately are back at your previous position. This is a process called backtracking. And now that we're at now that we backtracked one position, there might be new choices. If there's not, we're just going to keep backtracking until there is a new choice. We'll keep popping off the stack until we can push back onto the stack again. This is called a process called depth first search. You'll be using this algorithm to solve this maze, which is actually a bit easier than the other problem that's here for extra credit. Which is using depth first search to create a maze. It's the same algorithm, but it's a bit trickier when you're it's a bit trickier when you're solving the maze. I'm sorry, when you're generating the maze. So, but the same algorithm again is useful for generating a maze. Right? So here we are. Let's take a look at this algorithm. So what it's been doing here is that this is our. Let's go ahead and back up for a second. Okay. What it's doing is that it's basically randomly choosing a direction to go. And when it hits a dead end, it immediately fills in blue, right? See here, it tries to go in, and when it can't fill in anymore, it backtracks. And that's how it generates the maze. It goes forwards in random directions until it gets itself stuck into a dead end, and when it's stuck into a dead end, it backtracks until it finds new places to go. And that's how depth first search works. Make sense? So that's using it for maze generation. And there's a whole lot of different maze generation algorithms out there. But maze solving algorithms are very similar for this maze with 2 solutions. Very, very big maze. Let's see. It's traversing it using the right-hand rule, which is perfectly fine. But recursive algorithm over here. No, doesn't have an animation for depth first search, unfortunately. But it's straightforward. You just simply go down corridors until you hit a dead end, and then you back up. Right. So, yes.
Is there a cap for the stack? How many values they can hold?
Like, I'm pretty sure it's very, 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 very high. But you're only limited by Java, by the internal restrictions put in by Java.